Good day again, this is Klaus-Dieter. Back to my lecture, Mechanical Behavior of Materials, course number 315008, and we are in the spring semester 2022. This chapter is about dislocation theory. And today, I'd like to introduce plastic deformation of single crystals by slip. So what is slip? Slip is where we have the deformation of the single crystal as shown here to the left. We apply a tensile force across the specimen and eventually we get this plastic deformation, namely along some crystallographic planes we get dislocations by slip. Dislocation slip, which I have shown in the past lectures. So we get the dislocation movement and then we get these steps at the surface, which is plastic deformation. Now, how can we characterize quantitatively the stresses we need for slip to occur? Let's consider the scheme to the right here. So we have the slip plane shown in yellow, and we have the slip plane normal here in blue, and a slip direction P shown here in red. They are not necessarily coplanar. Then we define a slip system by the slip plane and the slip direction. And there are several such systems in the crystal. So let me remind, we have here the round brackets and we have the square brackets for the directions. If you look up the nomenclature as defined by the International Union of Crystallography, then a symbol such as HKL or 1, 2, 3, without brackets it would be a Bragg reflection, so a reflection of electrons, of X-rays, of neutrons. As last week in the characterization we talked about scattering vectors, and there we would not put a bracket around the HKL. Then we have the HKL with the round bracket designating a plane or a set of planes. So these are well-defined planes or a set of planes stacked in one orientation. Or we have the square brackets, they designate a direction in the crystal. So UVW or 1, 2, 3 is a direction in the crystal lattice. Furthermore, we have now equivalent planes. That means in a cubic, for example, the 1, 1, 1 plane and the minus 1, 1, 1 plane and the minus 1, 1 plane and 1, minus 1, 1 plane. They are all of the same type, but they have different orientations. So in space they have different orientations, but they're the same type of planes due to the symmetry of the crystal, and we call them equivalent planes and put them into these curly brackets. And finally, if we have crystallographically equivalent directions, like the A direction and the B direction in a tetragonal system, then by symmetry they look the same, but of course they have an angle of 90 degrees to each other. However, the one direction, if I sit and go in the one direction or sit and go in the other direction, they look the same. The surrounding looks the same. And we call this equivalent directions and put them into these triangular brackets. Good. Here, for example, I give the example of the FCC system. We have slip planes. Generally, the slip planes in a crystal, they have the highest planar density or close to the highest planar density. And that also corresponds automatically to the most widely spaced planes. So it makes sense. If the spacing of the planes is wider, then it's easier to apply the shear. In contrast, the slip directions, they have the highest linear density. So this is where the atoms, in this case, they touch each other. They're closest together. And that means we have the smallest Burgers vector. So we need only the smallest displacement in this direction. So highest linear density. We will see later on that the energy of the dislocation depends on the Burgers vector square. So if you have a larger displacement, then it costs a lot more of energy. And that defines a slip system. So we have the slip plane and we have the slip direction. So both together we say this is a slip system. For example, the FCC unit cell has a slip system consisting of the 1, plane and the 1, 0 directions. So this is very general. Now you can work out how many slip systems we have in the FCC unit. Again, I emphasize the FCC geometry, so phase center cubic geometry. For those who haven't had crystallography, it's shown here. We have, you should know about it. We have this cubic unit cell, and then on the center of the faces we have extra atoms, and this is called phase center cubic. The slip plane is shown here by this colored triangle, which is a 1, plane. So this is a typical 1, plane, which is redrawn here, seen from its normal direction. And there we see this is a closed packed plane. That means the atoms, they touch each other and they are aligned in this triangular shape. And we see there's already equivalent direction, slip direction here, or if we go here, it's the same equivalent one, or if we go here, also by symmetry, it's the same. If we rotate the system by 120 degrees, the one goes into the other. So, in this one plane, we have 3 slip directions. We have, if this is a 1, plane, then we have a slip direction of -1, 1, 0, of 0, -1, 1, and -1, 0, 1. And the negative of that. So we only write them down once. In one direction, positive or negative direction. It's the same direction. The same system. Also, we have 4 1, planes. And each of the planes has the 3 0, 1, 1 directions. And now we can say the directions and the planes we designate with A, B, C, D for the planes and 1, 2, 3 for the 3 directions. And that gives us 12 possibilities. So 12 slip systems we have, like on the 1, 1 plane here. We have the 0, -1, 1, the 1, 0, -1, and the 1, 1, 0 directions. So now written out with square brackets. And here in round brackets we have also the -1, -1, 1 plane with those 3 specific directions. They're all equivalent. If we only write down the equivalents, then it's written like this and like this. But if we specify them, we get 12 different systems, 12 different combinations of the 4 orientations and the 3 slip directions. So this you have to be able to work out. The BCC system, so the body-centered cubic, you know, body-centered cubic, we have a cube here, and in the diagonal, in the center of the cube, in the volume center, not in the phase center, you have another extra atom. You know about it. So here it's a little bit more complicated because we don't have really this closed packed planes. It's not a closed packed structure, so we have to distinguish. There are few principal slit systems, but also other closed packed directions. For example, we have the 1, 1, 1 planes in the direction of minus 1, 1, 1, and that gives you 6 times 2 equals 12 slip systems. Then we have slip on the 2, 1, 1 planes in the same direction, minus 1, 1, 1 type, and that gives you 12 times 1 gives 12 possible slip systems. And third, we have the 3, 2, 1 planes, can be 1, 2, 3 or 3, 1, 2 and so on, in the direction of minus 1, 1, 1, and that gives us 24 slip systems. And which one is activated depends, while there's some activation energy, which one is easier, depends on the temperature, but also on the bonding of the atoms in that system. So here I have marked down which metals at room temperature typically deform in those various slip systems. For example, alpha iron, the BCC iron at room temperature, moly, titanium, tungsten, and the beta brass. So alpha iron uses this slip system, but also uses that slip system and the third one. Molybdenum only uses the 2 slip systems, tungsten also 2 slip systems, beta brass only 1, and if you go to natrium, sodium, and calcium, potassium, they use one of the other slip systems. So it depends very much on the nature of the finesse of the bonds and also thermal activation. Maybe it's difficult to imagine here these closed packed or these closed lines, these dense lines in the lattices on these slip planes. So I've drawn here these 3 typical slip planes in BCC system, for example in alpha iron. This is the 110 plane. So here we see the first one, this 110, and then the 211 and the 321. And all of these planes, they contain lines, so lines here with dense packing. So there's dense packing in this direction, there's dense packing, and there's dense packing. And that's always the same minus 1, 1, 1 type direction. So it's always the same type of direction, but in different planes. You see the lateral spacing of these lines is different for the 3 planes. However, along the minus 1, 1, 1 direction, we always have the same spacing. So you can imagine if you put a Burgers vector in here, put a Burgers vector in here or in there, in first order, it's the same amount, similar amount of energy we need, and how much energy we need depends minutely on the bonds between the atoms. So, I said we have a lot of slip systems, 48 slip systems possible for the BCC structure, for the 3 planes. So here I have the 110 plane, here the 112 plane, and here the many for the 123 planes. 123 has a lot, 24. So you should be able to work out a table with the 48 slip systems for the BCC structure, and the solution is given here. For each slip system we have to satisfy the condition, the U, they just call it U, I don't know why, times the V, this vector. The dot product has to be 0. So we see 1, 1, 0, dot 1 minus 1, 1 is 0. And you can work it out for all the others. Yeah, there's a 0 here, up to here there's always a 0 in the third, so you only need to check the first two. So 1 and minus 1, 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1, 1, 1. What's happening here? Must be minus 1 here. 1, 0, minus 1. And you work them out. So, check whether there's a mistake in this table. That's a little homework. If we go now to HCP, slip planes and directions, so this is one of the other 3 fundamental lattices, monoatomic lattices. We have the FCC, the BCC, and the HCP, hexagonal closed packed structure. So we know this is a hexagon, and the principal slip system, they can generally depend on the C over A ratio and of the relative orientation of the load to the slip planes. Of course, it depends on the relative orientation of the load of the slip planes, but also can depend on the C over A ratio, typically. And again, I will introduce 3 slip systems. There may be more, but I introduce 3 slip systems, and which one is activated depends on the temperature. They have some activation energy. How easy is to break a bond or not. So we have here, we call that basal, like the base of the prism. You see here, the unit cell forms a kind of a prism, and this is the base of the prism, this blue shaded area. So that's why we call it a basal plane, and this is basal slip. So the slip plane is the 0, 0, 1 plane, and the direction is the 1, 1, 0. 1, 1 minus 2, 0 if you take the 4 indices. So how many slip systems we have? We only have one basal plane. Yeah, there's no other basal, this type of plane in the HCP lattice. And then we have 3 directions. Actually, we would have 6 directions, but that is just plus and minus. So if we neglect the plus and minus, we only have 3 directions. So we have 3 slip systems. So 1 times 3 is 3 slip systems. And that occurs mainly when the C over A ratio is larger than 1.633. 1.633, that's the ideal C over A ratio in a real ideal closed packed structure. So those who did crystallography, they can calculate that ratio. It's a nice homework. Just look it up and do it. And these metals, if C over A is distorted and is larger than 1.633, then typically we get the basal system activated. For example, in metals like cadmium, zinc, magnesium, alpha titanium, beryllium, and of course there are more. Secondly, we can have this phase activated as a slip plane. So that would be a slip plane, and the slip direction is this. I don't work it out here, but the slip direction is always the same in these cases, yeah? They're A plus, so this direction is the A direction, this is the B direction, so A plus B slip. They go in the A plus B direction. In all three we have the same. And yeah, so if we look now, how many of this kind of planes we have? We have 3 planes which are independent. Here on the back side, this is the same as on the front side. So it's 3 independent, the one here, the second here, and the third there. So 3 planes times 1 slip direction gives you 3 possibilities. And this typically or can be activated in titanium. You see, titanium can slip here on the basal, but also can slip on this side. And now I want to ask you how you call it. I said already this looks like a prism. So this is the face of the prism. So we call it prismatic. Prismatic. This is prismatic slip. Vocabulary: basal slip, prismatic slip. And this one, this is where the plane is inclined like this. So we have A and B direction, so A component, and we have a C component. So the normal of that plane has an A component and has a C component. So it's somehow inclined like this in the prism. And that looks like, if we continue like this, yeah, looks like the Egyptian pyramids. So we call this pyramidal. Pyramidal. So, very important, we have basal slip, we have prismatic slip, and we have pyramidal slip in hexagonal systems, particularly in the hexagonal close-packed system. And the pyramidal slip is often activated when C over A is smaller than 1.633, the ideal value, such as in magnesium or titanium. Whoa. Yeah, titanium we have here, titanium we have here. It depends also very much on the composition. This is a general rule of thumb, but which system is really activated, you have to measure it or look it up in a table. And again, it minutely depends on temperature. So at room temperature, you may have one of these 3 slip systems or types activated, yeah. And at higher temperature, you may activate the one, and at even higher temperature, you may activate the other one as well, and have them all. So, this table combines a little what I've said before for various metals. So we have here the FCC, face-centered cubic, close-packed, face-centered cubic, like copper, aluminium, nickel, silver, gold. And they have the slip plane of type 111 and the slip direction 1, -1, 0. Of course, we could write 110. We can write that down. but we want to help our brain already a little bit and put the minus sign above one of the ones, because then the dot product of this with the slip plane already gives 0. This is what we want, right? But it also would be a 1, 1, 0 type, because the type, these triangular brackets, gives you the family of the orientation vectors. And that gives you 12 slip systems. So we have 4 planes, and in each plane we have 3 directions, gives 12 slip systems. Then we have there's no silicon, right? Silicon is also FCC, but it's not close packed. We know it has a diamond structure. It may also have these slip systems, but it is not shown in this table because we are talking about the FCC close packed and the simple body-centered cubic listed here. So we have all the iron. The iron slips with anything. So it slips on the 1, 1, 0 plane, on the 2, 1, 1 plane, and on the 3, 2, 1 plane, which gives us 48 slip systems for iron. We know iron also is pretty ductile. If we only look to the 1, 1, 0 slip plane, then we get 12. If we look to the 2, 1, 1, we also get 12 slip systems. And if we look to the 3, 2, 1, that's the low symmetry, so we get 24 of these systems possible. So we have a lot of possible deformation in systems in body-centered cubic material. Now, let's go back to the HCP, hexagonal close packed. Then we have the basal system, we have the prismatic system, and we have the pyramidal system, all slipping in the same direction. But now we see here we have only 3, and we have 6 slip systems. So if we look up cadmium, zinc, beryllium, also magnesium at low temperature, it only works on one of the slip systems. I think the basal. Magnesium at low temperature. Then we only activate 3 slip systems, or we only have 3 slip systems. But it can be shown that at least you need 5 mechanisms, ways of deformation for continuity in plasticity. So here only 3, and that makes the material very brittle. So material becomes brittle because I do not have enough number of slip systems to accommodate plastic deformation continuously at grain boundaries, let's say. So then if I can, if one slip system hits the grain boundary, it cannot propagate or activate another system in the neighbor grain, and then it opens a gap and breaks. That makes material brittle. If we go to high temperature magnesium, then we have 2 or even 3 slip systems activated. And then even magnesium becomes ductile at 400 centigrade, 350 centigrade. It's ductile. If you go to room temperature, it's very brittle. There's another deformation process we are not talking so much in this lesson here, in this lecture, which is twinning, crystallographic twinning. So, the other BCC and FCC metals, they have many possible slip systems, and therefore the material is ductile. Now I have a 5 minutes break because there's noise outside on the road. Great, so I introduced the slip systems. You may have heard about them already before. And now, what do we need to move dislocations? If we slip, we need to move dislocations. We said the slip is by dislocations, not by solid deformation of the lattice planes. But what we need is a shear stress. And the shear stress is defined by the force divided by the area. Of course, the force is parallel in plane, so perpendicular to the area normal. Now, if we look to the situation of this yellow plane in our tensile specimen, then the component of the force in the slip direction is F times cosine lambda. If this is the angle lambda between the slip direction and the applied force here. So this is F times cosine lambda. Well, if it's going up, then it's big. If it's perpendicular, then it becomes 0. And the area, we also have to account that the area becomes larger when we incline it, and this scales with A0 or A here, divided by cosine of the angle of the inclination angle of the plane phi. So A over cosine phi. So let's put these two together. Then the shear stress tau resolved on the slip plane in the slip direction becomes tau equals the force divided by A cosine phi cosine lambda. And this is sigma, the applied force, divided by sigma times cosine phi cosine lambda. And this we call the Schmidt factor. Note that phi plus lambda is not 90 degree because the tensor axis slip plane normal and slip direction do not always lie in the same plane. So this is not necessary. Only if they lie in the same plane, then phi plus lambda becomes 90 degree. Otherwise, they can be different. They are not coplanar. The critical resolved shear stress, tau CRSS, critical resolved shear stress, this is the minimum stress required to begin plastic deformation. So we have the resolved shear stress, as shown in the previous slide, with the cosines. And now, when does plastic flow start? At the critical stress, so we call this the critical resolved shear stress. And this is temperature, strain rate, and material dependent. And the system on which slip occurs has the largest Schmidt factor. Yeah, so this is the point I want to make. The system on which slip occurs has the largest Schmidt factor. So we can have several planes. Yeah, we can have one plane like this. We can have one plane like this. And for each of the planes, we would calculate the Schmidt factor. And when it is those plane which has the largest Schmidt factor will be the first plane to yield with the critical resolved shear stress. So the stress tau is F over A cos phi cos lambda equals sigma cos phi cos lambda. The minimum shear stress to begin yielding occurs when lambda equals phi equals 45 degree, and then sigma equals 2 times tau CRSS. So in other words, if we have the plane here at 45 degree, and we have also the slip direction within the plane at 45 degree, so the plane normal is this, and the slip direction normal is this, and both are 45 degree, then we get the minimum stress to be applied by given critical resolved shear stress on the plane. So again, let's look it up here. A, the area scales with A over cosine phi, the applied stress P or force scales with cosine phi, lambda, and where the angle is lambda here, and shear stress is P over A. So the resolved shear stress becomes P over A times cos, here the formulas are written nicer, cos of the 2, which is, this is sigma 0 times cos phi cos lambda, or sigma 0 equals critical resolved shear stress divided by the cosines. And these cosines, they occur everywhere, and we call this M, this product of the two cosines, we call M, the Schmidt factor. So if we talk about the Schmidt factor, this is the product of the cosines. And this you need to know. This formula on this slide you have to know. So please learn it. So A is a slip plane, and here these are the angles. And sigma 0, this is when it starts to flow. So this is the critical resolved shear stress divided by these cosines. I think that's why they put the primes there for the critical. And so we measure, for example, the sigma 0 here, and then we can work out the critical resolved shear stress on the planes in our specific experiments. So it depends in the experiment on the orientation of the single crystal, of course. And here it's orientation dependent in the figure. So we know already for phi equals 45 degree and lambda equals 45 degree, the Schmidt factor becomes large, maximum 0.5. This is the maximum value, and this at this maximum value we need the smallest sigma 0 to yield the material, and this is nothing else but Tresca's criterion. Remember Tresca criterion? We had this yielding surface, and it was something like that. So here we have the sigma, the x and the y direction. So yielding in this, when you're outside this area, and we see here in the 45 direction, we get a maximum. In this direction, we get the minimum. Yeah, so the Tresca criterion corresponds when phi and lambda are 45 degree. So of course Tresca tells us when what is the minimum safest sigma which I can apply before a material can yield or starts to yield. Here in this figure there's a variation of sigma critical with orientation. So at Schmidt factor 0.5, the two at 45 degree, we have the minimum, and then we see when the planes become more inclined or less inclined, then we need higher stresses, we go to the hard orientations where the slip plane at 90 degree to the tensile axis is shown here. So what does this mean? If here we have a slip direction, let's say slip direction is like that inside that plane, but there's no critical resolved stress across the plane, because on the left hand side, on the right hand side, there is no shear stress resulting when the orientation is 90 degree. Or can imagine like this: on the left hand side you pull up, on the right hand side you pull up, there's no shear stress, both sides pull up. And the same if the plane is horizontal, yeah, you pull in this direction P outside, but you want to slip in this direction. Now there's a competition between slipping left or slipping to the right hand side, so it does not slip. You don't have a force projected onto the area, no force component projected onto this plane. So that when it becomes hard, 90 degree at 0, what is this? Here and here. Just looking to the other figures, looks all good. There are typical examples you should be able to solve. For example, calculate the tensile stress that is applied to the 1 minus 2, 0 axis of a gold crystal. You have gold all in your pocket right now. With inflation, you better buy some. To cause slip in the 1 minus 1, 1, 0 minus 1, 1 slip system. So this is the slip system. And what tensile stress you need to apply if the critical resolved shear stress is 10 megapascal. So at 10 megapascal critical resolved shear stress, it starts to slip. Resolved shear stress 10 megapascal, it starts to slip, so that's the critical resolved shear stress. Here's a little sketch, yeah. But what we do, you can do the sketch, it's always good to have a sketch. So you have the 1, 1, 1 plane normal here, and within that plane you have the 0, minus 1, 1 direction. And what we need now is these two angles, is this angle and is that angle lambda. So it's the angle phi and it is the angle lambda. To calculate the angles, we have, the normal of the slip plane, 1 minus 1 minus 1 is, and you know, the angle is the dot product. The angle is the dot product of 1, 1, 1 minus 1 minus 1, dot 1 minus 2, 0, divided by the square root of the lengths of the two. Yeah, so these are the absolute. Put the lengths. And that works out here. Here you do the dot product divided by the lengths, and you get 3 over square root 15 for the cosine phi. And then you do the same, the angle between the tensile axis, 1 minus 2, 0, and the slip direction, 0 minus 1, 1, is this. So it's dot product divided by the lengths of the vectors, gives 2 over square root 10. So these are the cosines. Dot product, they contain the cosines already. And now, since the critical resolved shear stress is 10 megapascal, so the applied stress is P over A is tau critical resolved shear stress divided by the direction cosines, and you put the direction cosines in here, and get a result of 20.41 megapascal. I guess you get homework with this and tutorials, but it's really good exercise to go through this. This is the solution example for these kind of questions. I mentioned already the system, will it be brittle or ductile? And whether it's brittle or ductile depends on a lot of factors. So it depends on the atomistic bond. So it's a potential function between the binding atoms. For example, if you have an oxide, silicon oxide, then you have these strong covalent bonds, and they're very narrow in length. So if you open them, you destroy them, and that gives you a brittle material. Or if it's shallow, so the bond strength doesn't matter so much on the distance, like in the metal, then it becomes ductile. Also recently I introduced the dislocation core. So is it wide or narrow? We had this Piles-Nabarro stress, those slides. So in a wide dislocation core, then it's easy to swap the atoms without having too much distortions on neighboring planes. And if it's narrow, of course, then switching the bond from one to the next influences a lot the neighbors, displaces or needs a lot of displacement of the neighbors, and needs more energy, and then it becomes brittle. So this is on a atomistic model, on the dislocation line model, and then on the mesoscale. So the number of active slip systems, which is also given by crystallography, but also by temperature. And if the number is less than 5, then materials tend to be very brittle. And if you have a lot, 12 or 24 or even 48 systems, then the material is ductile. All right, how much time we have? 11:38. Maybe I stop here today. I introduced the Schmidt factor, critical resolved shear stresses, some examples, and next time I like to introduce the analysis of stresses near the dislocation cores. Thank you very much.